I will speak on new algorithms for all pairs approximate shortest path. The all pairs shortest path problem is defined here on unweighted undirected graph. The graph has set of vertices V of n vertices and a set of edges E of m edges. And the output is a matrix in which in each entry UV we have the shortest path length between U and V. A natural algorithm for that is the naive BFS, breadth first search, apply it n times, and you get the solution. A more sophisticated solution is the seminal result by Zaidel, where he showed that using fast matrix multiplication, you can get a faster running time. These are the running time, and no progress, significant progress in the running time were obtained in the last couple of decades. So people consider a problem relaxation, the all pairs approximate shortest path, where the input is the same, but the output is a matrix that contain an approximation between every pair of vertices, where in approximation, we mean instead of computing DUV, where we omit G because it's clear from the context, we compute hat D of UV, and we say that it's an alpha beta approximation if it satisfies that it is at least the distance and at most alpha times the distance plus some beta. We refer to alpha as the multiplicative approximation and to beta as the additive approximation. And notice that if alpha is 1, then the approximation is pure additive, and if beta is 0, then the approximation is pure multiplicative. So this is a very short list of the history, which is relevant directly to this talk. Engworth et al. Initiate the research on this subject, and they obtain an additive 2 approximation in n to 2.5. running time. Dor, Halperin, and Zwick short after that improve it and get a improvement both for sparse and dense graphs. Since then, nothing is known. Dor, Halperin, and Zwick also improved or obtained a general trade-off. They also get a multiplicative approximation result with a multiplicative error of 3. And this is in n squared time. This was improved by Berman and Kasivastan, where they obtain an alpha beta approximation to 1. Baswan and Kavita got a multiplicative 2, but they have the running time is n squared plus m square root of n. Most recently, Deng et al. Obtained an strict improvement to Dor, Halperin, and Zwick, but they used fast matrix multiplication, where we don't really like to use it. One thing on the general trade of Dor, Halperin, and Zwick, the k must be even. So let's see what we can understand from this table. So the main open problem is, can we compute an additive 2 approximation faster than Dor, Halperin, and Zwick without fast matrix multiplication? Before we even start to answer this question, maybe we should check what is the relation between additive and multiplicative approximations. So can we compute 2-0 multiplicative 2 approximation faster than additive 2 approximation? So a simple observation shows that if we have a 1-2 approximation, then we can simply obtain a 2-0 approximation for it, because a 1-2 approximation is a multiplicative 2 approximation for every pair of vertices that do not share an edge, and checking whether there is an edge or not is linear in the number of edges, so we can get this relation. So what we can get from the existing result is that we can get a multiplicative 2 approximation in the running time, which is the minimum between Baswan and Kavita's result and the Dor, Halperin, and Zwick result for dense graph. So, and this will be the cutoff in which of the 2 algorithms we are going to use. So the result that we just out of the box using the techniques that we have is this. The question is, can we do better? So let's look a bit closer in this observation. And a more general way to say this observation is the following. So an additive K approximation is simply a 2-0 approximation for every pair of vertices at distance at least K. So if you take Dor, Halperin, and Zwick, this is what we get. So for every pair of vertices of distance at least K, we have a 2-0 approximation in this running time, where you can see that the larger K became, we get a better running time. So this gives the inspiration for the following framework for a 2-0 approximation. Divide the situation into two cases where you deal with sparse graph, you deal with the Baswana-Kavitas algorithm. Here we cut it in n to 7/4, but it doesn't really matter why it's n 7/4 for now. And for dense graph, try to use the algorithm of Dor, Halperin, and Zwick with the larger K that you can. So here we use 4 and see what happens. So if we use 4, so here it's the running time for the sparse case, here is the running time for the dense case. And if we plug here 4, then you can see that we get an improved running time. It's for dense case, it's this, which is much better. But we are missing some information because for distances 3 and less, we don't have a multiplicative 2 approximation. So what we can do, this is what I will show you in the rest of this talk, how we can get an additive 2 approximation for distances which are at most 3. So the answer for this question is yes, and we need to show how you can compute an additive 2 approximation for the very restricted case where the distances are at most 3 in time which is faster than n to 7/3. So the first result is that we can do this in time, in this running time. And the outcome of this result is that we can get 2-0 approximation in a better running time for the dense case. So inspired by the previous discussion, a more general question that we can ask on Dor, Halperin, and Zwick algorithm is the following. Can we improve the running time, the approximation from 1K to 1K minus 2? Remember, it's only even case, and keep the running time the same. This will be a strict improvement to Dor, Halperin, and Zwick, but this is very hard. We don't know how to do it. So let's make our life a bit easier and say that we do it only for a certain distances, only for 2 vertices that are a distance at most C for some C. And result 1 partially answers this question for these parameters, and result 2 is the following. When K is at least 6 and we only consider distances that are at most K, we can get a K minus 2 approximation instead of a K approximation, an additive K minus 2 approximation instead of an additive K approximation. So this is the second result in this paper. And for the rest of this talk, we have the following roadmap. So we will, I will try to give you the picture for the additive 2 approximation for distances at most 3. In order to do that, we need to understand some essential details from Dor, Halperin, and Zwick K algorithm, the first one, the one for sparse graphs. Then I will show you how to use Dor, Halperin, and Zwick algorithm with hierarchy of 4 sets. It will be clear in a moment what I mean by a hierarchy in this algorithm. And finally, we will go through the ideas that are needed in order to get an additive 2 approximation fast for distances at most 3. So this is the roadmap for the rest of the talk. So let's start with the essentials of Dor, Halperin, and Zwick's algorithm. So some definitions. For every vertex U, we have a set N of U, which is the set of neighbors of U. And we have T numbers, where we call them Z1 until ZT. And this T will be the number of the size of the hierarchy, the number of levels that we have in the hierarchy that we will create in a moment. And Z2 is always 1. Now we have we divide the vertex set into T sets, where V1 contains all the vertices that their degree is very high, it's at least Z1, and so on. So as you can see from this definition, V1 is a very small set because we have it there only vertices that have a very high degree, and V2 is a bit larger until VT becomes the entire set of vertices. The edge set will be as follows. So let's look on F2, for example. F2 contains all the edges that one of their endpoints is of degree at most Z1. Okay, so this means that when we look on F1, I didn't really define Z0, we just plug there E, and F2 has less sets, but it's still less edges, but it's still a very large set. And we go on until we get to FT, which is very small set. Okay. Finally, we have the heating sets. These sets are supposed to heat the neighbor sets with respect to the size of the neighbor set. The size of Zi is n over Zi. And the requirement for this set is that if the degree of a vertex is at least Zi, then the set Zi contains one of the neighbors of U. A bit more notation, Q S Zi is a set that contains all the vertices that S is the representative in Zi. Okay, this S is the vertex that hits the neighbors of U. In that case, if U is in the set Q. Let's see an example. So here's the vertex V. We say that V, we assume V is of degree at least Zi and at most Zi minus 1. So we can understand from that several things. The first is that V is in Vi, as I said, and because it has at least Zi edges, then a vertex in Zi, the set Zi, is one of its neighbors. This is W. And because V is of degree at most Zi minus 1, then all the edges of V are in Fi. And finally, we add for every vertex V the edge that connects it to the vertex that hits it. So this is not too much, just understand that just remember that we do this, it's order of n anyway. So we do it for every set, and we always have these edges, we really need them. The algorithm outputs a matrix M where XY contains the approximation, the entry XY contains the approximation that we have for XY. But this is not just an output matrix, it's also a matrix that is being updated through the running time of the algorithm. And when we run Dijkstra's, you will see in a moment, then we take from this matrix a weight for the edges that we add to the source from which we run the Dijkstra. So if we run a Dijkstra from a vertex U, we assume that U has an edge to each vertex in the graph, and the weight of the edge is the value that we currently have in the matrix M. Okay, so we're also going to use this. So other than all these definitions, which are quite confusing, the algorithm itself is very simple. We just have t iterations, and in the ith iteration, we run on all the vertices in Zi. And for each vertex like that, we run Dijkstra in a special graph. The graph is composed of shortcut edges that we add from U to each vertex of the graph, whose weight is being taken from the matrix M, the current value that we have there. The edge set E star, which denotes simply all the edges between vertices and their heating vertex. and the set Fi, which we defined in the previous slide. And after we do this Dijkstra, we simply update for every x in the graph the current estimation in the matrix with respect to the vertex u. Dor, Halperin, and Zwick proved the following. If Mi is the matrix after the ith iteration, then you can show that for a vertex u in the set Zi, after running the ith iteration, the distance between the estimation to the distance between u and v is at most the distance plus 2 times I minus 1. And since the last iteration, the set Zt is simply v, if we plug it in the lemma, we get that the approximation is 2 times t minus 1, and 2 times t minus 1 is simply our k, and t is the number of hierarchy, the size of the hierarchy that we have. Finally, the running time is very easy to see, is simply this. Because in each step of the iteration, the most time-consuming step is doing the Dijkstra for Zi, for the set Zi in the graph whose size is dominated by the size of the set Fi. Okay, so this is what we have in Dor, Halperin, and Zwick algorithm. So let's see what we can say when t is equal to 4. When t is equal to 4, it means that we have 4 numbers, where the last one, the Z4, is 1. And we have this color map here to help you understand or to remember which set is large and which set is small. So let's see, V1 will be a small set because it only contains the vertices of degree at least Z1. V2 is a bit larger, and V3 is also a bit larger, and V4 is simply the entire vertex. With the edge set, we have the opposite direction. So F2 is large, F1 is simply the entire set, F4 is the smallest. Okay, and for the Z, so Z1 shouldn't be too large because it only has to, it's very easy to hit a large neighborhood with small number of vertices and so on. So this is the relations. So our algorithm will do the following. So from now on, just fix 2 vertices in your mind and call their shortest path PUV. And now we run Dor, Halperin, and Zwick's algorithm with t equals 4 and see what we can do. Some of the information we already have a very good estimation that we don't really need to do anything. Some we have to do some tricks, and some we have to do more tricks. So this is the rest of the talk, and these are all new ideas. And let's see how we are going to deal with distance S3. So we have 3 cases. The first case is that the shortest path between u and v has no vertex, as a vertex from v1, which is a vertex of high degree, so it's red. The second case is that we are not in the first case, so no vertex is of high degree, but either the u endpoint or v endpoint is of a medium degree, so they are in v2. And the third case is that we are not in the first and the second, and we have here 2 subcases. Either case A, either both u and v are not in, even not in v3, so we are in this case, or one of them is in v3, and we are in this case. Okay, so let's see what we can say on each one of these cases, how we can deal with them. So the first case is kind of easy case because we have a very high degree vertex on the path. And this means that for this vertex, we know a very good estimation on the distance from the neighbors of this vertex. And what we do in our algorithm, we just improve for every pair of vertices the estimation that we have by going on all pair of vertices and improving through the vertex set of Z1. The cost of that is n squared times z1, and obviously the cost from Dor-Halperin and Zwick that we put it here as well. The approximation be as follows. So for the vertex A star 1, which is hits the red vertex A, we know the exact distance both to U and to V. And this exact distance is an additive, is at most +1, the distance between U and A, and the distance between V and A. It's a typo here. And if we take this, we get an approximation of 2. A bit more interesting case is when we are in this case. In this case, what we have is that we know, because C1 doesn't hold, we know that the degree of all the vertices in the path is at most Z1, which means that all the vertices on the path are in F2. So when we compute for U star 2, or for every vertex in Z2, we get the exact distance from, we get a distance which is +1, the exact distance between U and V. And what we now have to do is just to improve the distance, the estimation that we have for U. So we do it by taking the distance from the vertex that hit U and add 1 to it. This is the cost, and this is the approximation. Okay. The most interesting case is case 3. So in the first subcase A, we have the following assumption. We assume the degree of A is the largest. And if this is the largest degree and it's still less than Z3, then we are in a very good situation, because we have the exact distance computed from U and from V when we run it for Dor-Halperin and Zwick, because all these edges are in F4, which is E. If it's not the case, it means that the degree of A is at least Z3. It might be also Z2. It is less than Z1. So we are in this case. And in this case, so when Dor-Halperin and Zwick computes, they get the exact distance between A star and A star 2 or 3 to V. And in the fourth iteration, what happened is that we have this shortcut edge from V to A star 3 or maybe A star 2, and the edge that connects it to A is also in E star, and we have the edge between A and U, an edge in F4, because U is of a small degree. Okay. So this gives us an additive 2 approximation. Finally, we get to the last subcase, which is the most sophisticated one. And here we have this situation. So because we know that U is in V3, it has some vertex that is in Z3. It's not enough, but it gives us something. If we compute the distance between the BFS from every U up to depth 2, just in the graph that contains the vertices that are not in V1, then we get an additive, we get the exact distance from U to B. Now we improve this distance by doing the following steps. We take for every vertex in Z3 and go through all the vertices here, U, W, and Z, that are the vertices that are in the set Q, S, Z3. And we go through all these vertices and take the best estimation to every other vertex in the graph. So in this case, the distance between U and B is 2, so we get for U star 3, we get a distance 3 in the matrix. Then we run Dijkstra from S. This gives us that from U star 3, we get an estimation of 4, we get estimation of 4 in the matrix to V. Finally, for every pair of vertices, we improve the distance through the vertex that hits them in Z3 and get the running time, the estimation that we need, which is 5. The running time is this. So the first is NZ2Z1, and the second is trivial. Is not trivial, it's a bit more specific, but it's not hard to see that it's n squared, and the third is trivial. Okay, that's all. We just set these values to z and get the desired running time.